Welcome to the second video. In this video, we introduce inner products. The inner product you can think of as a generalization of the dot product that you have seen in R2 or in R3. For two vectors in R2 and R3, you must have studied u dot v if u and v are vectors in R2 or R3. The inner product is a generalization of this concept to the entire Fn, Cn or Rn. Now take two vectors u equal to a1 up to an and v equal to b1 up to bn in Fn. Define the inner product uv as a1 b1 bar plus etc. an bn bar. So if all the ai's and bi's are in R, that is f is equal to R, then the inner product uv is given as a1 b1 plus etc. an bn. So if you take n equal to 2 or 3, this is nothing but the usual dot product that you have studied in your school. If you take u equal to 1 2 3 and v equal to 2 1 3 in R3, then the inner product you get it as equal to 13. Similarly, if you take x to be equal to 1 plus I 2 minus I 1 and y is 1 minus I 1 plus I and 1, then their inner product, as you can see, is equal to 2 minus I. You can think of this vectors, the vectors in Fn, either as an element of F1 cross n or as an element of Fn cross 1. You can think of it as a row matrix or a column matrix. Then you can define the inner product in this manner. If you take u and v to be elements of F1 cross n, then define the inner product uv to be equal to u v star. So v star is conjugate transpose of v. So if u is a1 up to an, the 1 cross n matrix, and v is b1 up to bn, then uv star is nothing but a1 b1 bar plus etc. an bn bar. Similarly, if u and v are vectors in Fn cross 1, matrices in Fn cross 1, then you define inner product uv to be equal to v star u. In this also you can see the definition coincides with the usual inner product definition of vectors. The inner product satisfy some of very basic properties which all of them follow from the definition. For any x, y, z in Fn and alpha, beta scalars in F, you can see that the inner product satisfy all those 7 properties that is listed. Inner product of xx is bigger than or equal to 0, and it is 0 if and only if x is 0. And both these directly follow from the definition. You just apply the definition and what you get are these properties. So we recommend that you verify each of these properties by hand, writing it down and verifying it for yourself. These are all easy verifications and we leave it to you to complete it. Using this inner product, one can define norm of a vector. The norm of a vector is again, it's a generalization of length of vector in R2 or R3. In R2 or R3 we have seen length of vector which is equal to the, if you take a vector u1 u2 u3 a1 a2 a3 vector in R3, the length of this vector is square root of a1 square plus a2 square plus a3 square. Now if I take a vector u in Fn, define its norm as norm of u equal to square root of inner product u. So if u is a vector in Rn, this coincides with our definition of length of a vector. Now if u is a vector in Cn, this again is given as norm of u equal to square root of a1 bar plus etc. an bar, which is nothing but square root of mod a1 square plus etc. mod an square. For example, if u is a vector in R3 1 2 3, then norm of u is square root of 14. Similarly, v is 2 3 4, then its norm is square root of 29. X is 1 plus I 2 minus I 1, then norm of x is square root of 8, and similarly norm of y is square root of 5. As in the case of inner product, norm also satisfy some basic properties. Norm of x is non-negative real number. It is 0 if and only if x is 0. This follows directly from the property of inner product, definition in fact. Norm of alpha times x is mod alpha times norm x. The next two properties, called Cauchy-Schwarz inequality and triangle inequality. Mod of inner product xy is less than or equal to norm of x times norm of y. That's called Cauchy-Schwarz inequality. And norm of x plus y is less than or equal to norm of x plus norm of y. This is called triangle inequality. We will prove both these inequalities. If y is 0, then inner product xy is 0 and norm x times norm y is also 0. So therefore Cauchy-Schwarz inequality holds true. Suppose y is non-zero, which means inner product y is non-zero. Take alpha to be equal to inner product xy divided by inner product yy. Then alpha bar is inner product yx divided by inner product yy, and alpha bar times inner product xy is nothing but mod alpha square times norm y square. This can be easily verified. So therefore one can see that alpha bar times inner product yy minus inner product yx is 0. Now look at this vector x minus alpha y. X minus alpha y is a vector in Fn. Therefore its inner product with itself is non-negative, that is 0 less than or equal to inner product x minus alpha y, x minus alpha y. Expand using the properties of inner products, cancel off the 0 term and then simplify. What you get is precisely the Cauchy-Schwarz inequality. Now let's come to the proof of triangle inequality. norm of x plus y square is equal to inner product x plus y, which is equal to norm x square plus norm y square plus inner product xy plus inner product yx. Now inner product xy plus inner product yx, this is equal to twice the real part of inner product xy, because inner product yx is inner product xy bar. And using Cauchy-Schwarz inequality, we can say that the real part of inner product xy is less than equal to mod of inner product xy, which is less than equal to norm x times norm y by Cauchy-Schwarz. Therefore, norm x plus y the whole square is less than or equal to norm x square plus norm y square plus 2 times norm x times norm y, which is nothing but norm of x plus norm of y the whole square. Now taking positive square root, triangle inequality follows. If you take two vectors x and y in Fn, we say that these two vectors are orthogonal if inner product xy is equal to 0. We write this as x perp y. So x perp y if and only if inner product xy is 0. A quick observation is that the 0 vector is perpendicular or orthogonal to every vector. Now if you look at the expansion of norm of x plus y the whole square written above, you can immediately see that if x is orthogonal to y, then norm of x plus y square is equal to norm x square plus norm y square, because inner product xy is 0. This conclusion is called Pythagoras law. If x is orthogonal to y, then norm of x plus y square is equal to norm of x square plus norm of y square. The converse of Pythagoras law holds when f is equal to r, that is, if the vectors are in Rn. If you take x and y to be vectors in Rn, then norm x plus y square is equal to inner product x plus y with itself, which is equal to norm x square plus inner product xy plus inner product yx plus norm y square. This inner product xy plus inner product yx is same as 2 times inner product x comma y. But then this is equal to norm of x square plus norm of y square implies that inner product xy is 0. That is, x is orthogonal to y. This converse does not hold in general. That is, if f is equal to c, the converse statement is not true. You can easily see what the reason is. If you look at the expansion of inner product x plus y with itself, it is norm x square plus inner product xy plus inner product yx plus norm y square. Inner product yx is same as inner product xy bar when x and y are in Cn. Therefore, the sum of these two terms give you twice the real part of inner product xy. Now if norm of x plus y square is equal to norm of x square plus norm of y square, this implies that twice the real part of inner product x comma y is 0, or in other words, the real part of inner product xy is 0. this does not really imply that inner product of x comma y is 0. For example, if you take x is equal to 1 and y is equal to I, you can see that norm of x plus y square is equal to, which is equal to norm of x plus norm of y, norm of x square plus norm of y square. But at the same time, inner product 1 comma I is not equal to 0. Therefore, the converse of Pythagoras law does not hold when f is equal to c. Now we talk about adjoint and inner product. Suppose I take a matrix A in f m cross n, a vector x in f n cross 1 and y in f m cross 1. Then inner product ax with y is same as inner product of x with a star y. Similarly, inner product of a star y with x is same as inner product y a star ax. The proof is immediate from the definition. If I take a in f m cross n and x in f n cross 1, what you get, the vectors ax and y both are in f m cross 1. So therefore we can write the inner product ax comma y as y star ax. Now this, using associativity, you can write y star a times x, and y star a I can write it as a star times y whole star, and that is nothing but, by the definition, it is inner product x with a star y. In a similar manner you can get the next equality as well. We leave it to you to do it on your own. If A is a unitary or an orthogonal matrix, then inner product ax ay is same as inner product xy. This in particular says that norm of ax is equal to norm of x. The columns of A are all n cross 1 matrices. You can think of them as n cross 1 matrices. They are all of norm 1, and they are, two distinct columns are orthogonal to each other. And we have the same conclusion for the rows as well. So let's look at the proof. Inner product ax ay, using the previous theorem, you can write it as x times inner product of x with a star times ay, but a star a is equal to 1 identity, therefore it is equal to inner product xy. By taking x equal to y, we get the second equality, that is norm of ax. Norm of ax square is nothing but inner product ax which is same as inner product xx, which is same as norm x square. So therefore the second equality follows. Now A is a unitary matrix, therefore we can write A star A equal to identity. Now what is A star A? The ith row of A star multiplied with the jth column of A is the ijth entry of A star A. Now this is equal to delta ij, because in the identity matrix only the ith entries are non-zero, they are 1, and otherwise it is 0. But now the ith row of A star multiplying jth column of A is nothing but taking inner product of jth column of A with the ith column of A. That is 0 if I is not equal to j, and that is equal to 1 if I is equal to j. And that's exactly the conclusion of the second proposition, second statement. Similarly, one can prove the third statement. So this concludes the second video. We will come back with further topics in matrix theory.